my pleasure to introduce Mark Behrens, and you'll talk about the tmf-based atom spectral sequence for that.
I should have written this before, but I just realized I should write my collaborators down right now. This is joint work with Agnes Beaudry, Prasit Bhattacharya, Dominic Culver, and Zhouli Xu. Okay. How's that? Good. Okay.
Alrighty. So when I say TMF resolution, or I guess my title in the schedule is stated a little differently, I mean TMF atom spectral sequence. Okay? So the atom spectral sequence based on the cohomology theory, little tmf. Now this is inspired by, so a bit of background. This whole business is inspired by the work of Moholwald and his collaborators on what are called BO resolutions. So BO is otherwise known as little ko. It's connective K-theory. And this work, Moholwald did a lot of work with Davis, with Lellman, and other folks. And computed with this BO-based atom spectral sequence. That's what this really is, the BO-based atom spectral sequence. So it's some spectral sequence that I'll denote like this for, say, a spectrum X. And here, this entire talk, I should say, is at the prime 2. Okay? And this thing converges to the homotopy groups of the 2 completion of X. So I'll just write pi star X. Okay, so they scored a lot of successes with this spectral sequence. Did things like computed the V1 periodic homotopy groups of spheres, and in the process verified the telescope conjecture. For n equals 1 and p equals 2. The n equals 1, p equals odd telescope conjecture was verified by Haynes-Miller using a little bit different methods. And in addition, computed things about the image of J. And in general, did many computations, many unlocalized computations. You see, the BO-based atom spectral sequence is not just a device for computing V1 periodic things, but it's also good just for computing homotopy groups. It's something that was discovered was that the BO-based atom spectral sequence is very efficient. In fact, once you get its E2 term, it often has very few differentials. So there's very few differentials past the E2 term. The only problem is getting the E2 term is hard. Okay? And why is this hard? It's not hard like it's hard to compute the Adams-Novikov, the E2 term of the Adams-Novikov spectral sequence, and the E2 term of the Adams-Novikov spectral sequence is just arguably harder than the E2 term of the Adams spectral sequence. But it's hard for a different reason. It's hard because the E1 term is hard. I mean, when you're thinking atom spectral sequence, you're thinking, oh, the first thing I need to understand is I need to understand BO star BO. Okay? And this thing turns out to be messy. It's, in fact, really messy. And one problem it has is it's not flat over BO. So that means that the usual machinery that you use to compute the E2 term of an atom spectral sequence no longer applies in this setting, and you don't get an axed description of the E2 term. Okay. Okay. So we're going to encounter some similar problems. So what about this tmf-based atom spectral sequence, the tmf resolution? So I'll write this spectral sequence like this. You know, it has some ER pages. So you have a different one for every spectrum X, and this thing converges to the homotopy groups of X. All right, so what's up with this spectral sequence? Well, so here, let me just mention that this spectral sequence was already studied by Mahowald in the late 90s. And basically for the rest of his life, he was working on this thing and making a lot of progress on this. And I'll say that really the starting point for understanding something like this is to understand the analogous ring of cooperations, TMF star TMF. And this was studied by many people, both at odd primes and the prime 2. So this was studied by both Andy Baker and Gerrit Lores, and then Mark Mahowald, and most recently by myself and collaborators. So the paper is Kyle Ormsby, Nat Stapleton, and Vesna Stoyanowska. And let me just say that this thing is really messy. Okay? It's a real mess. In particular, it's not flat over TMF star, okay? But I mean, you probably guessed that already, all right? But you might think, gosh, you know, BO is kind of bad because it's got like these Z mod 2s. And you might think TMF is bad because it has like this whole mess of torsion, right? And maybe that's the reason that this is so bad. And I want to point out, no, that's actually only one of the reasons. That's actually not the worst thing about it, okay? So I want to point out that actually, even in the case where you consider BP brackets N, I'm going to write that over here. BP brackets N is already bad. So say you consider something like BP brackets N star, BP brackets N. Well, now BP brackets N, you know, it's torsion free, it's super nice, right? But BP brackets N star, BP brackets N is not so nice. This thing is not flat over BP brackets N star. And in fact, this thing has a bunch of torsion.
Mark?
Yeah?
When you say flat, is it faithful?
Is it so you want to know if it's faithful even though it's not flat? I have no idea. I can't parse the terminology, so I don't know. It has a
TMF star inside of it, so trouble.
Yeah, I mean BPN is a sum end of it, so it's.
That is true. Yeah. Okay. So already I'm rescued. Great. All right. So it has a bunch of it has a bunch of torsion inside of it. In fact, this thing was computed by Adams at the end of his Chicago notes for n equals 1. And he observes what this looks like. And n equals 2, the story is much more complicated, and that was done by Dominic Culver. Okay? And let me say a feature of what these things look like. Okay? So you take BP brackets n star BP brackets n, you can map it, you can invert Vn, map it to En star En, say. Okay? And then you can think about this thing. And so this thing is nice, okay? This is something like the Morava stabilizer algebra, and it's flat over En star. This is nice. And so the image in this thing is somewhat nice, okay? So this thing has some nice image, okay? So there's some nice image, which we'll call good, because it can be computed. And then there's some kernel. And at least in the cases of n equals 1 and n equals 2, it turns out that this kernel is a graded F2 vector space. That is all the VIs act trivially on it, okay? And this thing is totally incomputable. And so we call this thing evil, because it's so incomputable. So that's the kernel. Okay. Nevertheless, you can kind of, even if you can't compute it, you can kind of define the problem. So you can take, I guess, this E1 term of the BP brackets n atom spectral sequence. And you could do this not just for the one line, but for the n line, and you could map it to the corresponding thing. You could consider the image in the corresponding E1 term of the E parentheses n atom spectral sequence for X. So this thing has an image in here. So we'll call this the good complex. And then the kernel is this thing we'll call the evil complex. Okay, evil complex. And we can't compute it, but it's there. So this gives us a short exact sequence. And then we get a long exact sequence when we compute cohomology. You get a long exact sequence that will look like the E2 term. And it'll go to the cohomology of this good complex. And it'll involve the cohomology of this evil complex. And in previous work with these co-authors, we showed that that even though this V star X is really incomputable, its cohomology is actually computable, provided you're able to establish that it's that basically another way of saying what I was saying over here is that BP brackets n smash BP brackets n, at least for n equals 1 and n equals 2, probably for all n, but I mean, it was hard enough for Dominic to prove this for n equals 2, so maybe it's a harder thing to prove. This thing is equivalent to something wedge an Eilenberg-MacLane space for a graded F2 vector space. So the evil stuff is coming from here, and this is like the good stuff. Okay? And as long as you have such a decomposition, it turns out this thing is computable. And we use some tool that I'm not really going to talk about, something we call the Agatha-cockological spectral sequence. And whatever this thing is, it's something that will compute this from X. So it's like if you can compute X, you can compute this, is more or less the slogan. Okay. So that means, we've reduced this sort of evil problem to just sort of understanding X computations, and we're left with this good part. All right, so now I think it's time to talk about the problem at hand. So let me mention that we use this technique to do a bunch of computations in the BO case. We computed the E2 term of the BO-based atom spectral sequence of the sphere through some range. Okay. Great. Okay, so now it's time to talk about Z. So what is this Z? Okay. This spectrum has been studied extensively by Bhattacharya and Egger. So to explain why this is the guy, I have to tell you some things, okay? So first off, we already discussed in other talks how the mod 2 Morse spectrum doesn't have a V2 or V1 to the 1 self map, but Adams showed it had a V1 to the 4th self map. Okay? And then when you do this, you can take the cofiber, and I'll call the cofiber S mod 2 V1 to the 4th. Okay? And then this is a type 2 complex, and in joint work with Hill, Hopkins, and Mahowald, we showed that this guy has a V2 to the 32 self map, realizing the 192 periodicity in TMF. Okay, so that's complicated. It's big numbers. It's already feeling intimidating. It would be much simpler if we just had small numbers. So solution is to mod out by more stuff. So something that was observed early on in the subject was that if you take the sphere and mod out by 2 and eta, that is, take the cofiber of eta viewed as a self-map of the mod 2 Morse spectrum, or smash the cofiber of 2 in the cofiber of eta, however you want to think about it, this thing has a V2 to the 1 self-map. Or sorry, V1 to the 1 self-map. And this spectrum is called Y. Okay?
Why?
Exactly.
I don't know. We don't ask these questions. We just keep going. So now we want a V2 to the 1 self map, and this was the real work of these folks. So they observed that if you take this guy Y, then it has a V1 self-map, so I could mod out by it. And now I have a type 2 complex. Okay? It turns out in the homotopy groups of this type 2 complex, kappa bar has a 4th root. However, kappa bar to the 1/4 does not extend to a self-map. But after you mod out by nu, it does. So then you can quotient out by it. And this is the definition of Z. Okay, and they show that it has a V2 self-map. So that's the Z that I'm interested in. There's some other nice things about Y and Z that I should mention. So one nice feature of Y is that it gets rid of that nasty 2 torsion in BO. BO smash Y is connective Morava K1. And TMF smash Z is connective Morava K2. So it has a similar feature with respect to TMF. Using this fact, Bhattacharya-Egger did something else. They computed the capital TMF atom spectral sequence for Z. Technically speaking, they took one of those resolutions that Agnes was talking about and smashed it with Z and computed that. But that's more or less equivalent to what I'm saying over here. And this is the E2 term, obviously, of a spectral sequence, but now because of a capital TMF here, it turns out to converge to the K2 localization of Z. And so they computed this. And they observed that it was small. Okay, it's a nice, neat, compact little thing. And so there's not many room for differentials, but there is still room for some differentials. But nevertheless, they conjectured that this spectral sequence collapsed. However, a kind of version of this Z also showed up somewhere else in a different guise in work of Mahowald, Ravenel, and Schick. So they were interested in the telescope conjecture, and they were looking at a spectrum whose name was little y2. And I'm not going to really tell you what this is, except for the fact that it's closely related to Z, kind of like Z. It turns out to not be a finite complex, it's an infinite complex, but it's still kind of like Z, okay? Z maps to it, it's kind of nice, okay? And in particular, it has a very natural V2 to the 1 self-map. Just not finite, that's okay. And they were studying the telescope conjecture, which meant they were trying to compute the homotopy groups of the telescope of this map. And to do that, you can't use something like this. This is like what you get when you invert V2 on the on this spectral sequence. You can't invert V2 on like an Adams-Novikov type spectral sequence. It won't converge to the telescope. But it turns out that if you invert V2 on the Adams spectral sequence, it does converge. So they were studying this guy. Okay, and they computed this. In fact, they computed the E5 page modulo some things. I'll just say they computed the E5 page. And they observed that this E5 page is huge. It's large, okay? It's big. And this E5 page, well, they also conjecture that the spectral sequence collapses at E5. So then, this kind of thing tells you that the K2 localization has small homotopy, and if this conjecture were actually true, you would deduce that this homotopy was really big, and then they'd be in particular different, and so you will have disproved the telescope conjecture. So this would imply the telescope conjecture is false. But of course, they weren't able to prove this.
Mark, can I just ask that big TMF spectral sequence? So if you smash Z with big TMF, do you get a periodic K2, or do you get something else?
Yeah.
Right.
Mm-hmm.
Okay. So what do you get for the algebraic E2 term? Is there some description in terms of sort of TMF star TMF mod something? Is there some sort of?
Yeah. This turns out to have a nice description. It's. I mean, you know, it is. It turns out that this thing is actually. I'll come. Actually, I'm going to return to this point, Andy. But this what's going to turn out is that TMF smash K2 pi star of this turns out to be what really is the Morava stabilizer algebra. Yeah. Well, not exactly. I'm sorry. I made a little mistake. It's a subalgebra that I'm going to describe of the Morava stabilizer algebra. And I'm going to spend a little time describing this subalgebra. And it turns out that this E2 page is the cohomology of this subalgebra. Yeah, so no, that's good. I want to bring these things up. Yeah. Any other questions, comments? Okay. All right. So what do I want to do? So I want to set up the this TMF atom spectral sequence for Z. Try and understand the cohomology of the good complex, and we're going to do some low-dimensional computations. So we'll actually compute this spectral sequence through some range. And then what we're going to do is we're going to compare it with the TMF atom spectral sequence. And just our low-dimensional computations and having a map of spectral sequences is going to turn out to imply this conjecture of Bhattacharya-Egger. So this will imply that this Bhattacharya-Egger will imply the TMF atom spectral sequence for Z collapses. And that's already kind of nice because we're at p equals 2, where we supposedly can't do any chromatic 2 computations, and yet this, I think, completes maybe the first one. And then, at least for a finite complex. And then the third thing we're going to do is we're going to I'm going to make some comments on the telescope conjecture. Now, before you get too excited, spoiler alert, we're not going to disprove the telescope conjecture, okay? No. So we'll not disprove telescope conjecture. We're just going to kind of understand what the whole old Ravenel and Schick were doing and why it's so cool, okay? But we still have lots of questions. So in Toby's talk, he said the telescope conjecture is hard. And then he said it's also subtle. It's hard. But in addition to being hard, it's subtle. And we got to talking over dinner on Wednesday. We were like, what kind of problem is hard but not subtle? And we came to the conclusion that moving a huge boulder is hard, but it's not subtle. But having thought about this for a while, this telescope conjecture stuff, I'm going to report to you that it's about as gratifying to work on this conjecture as it is to try to move a huge boulder. Okay? All right. So let's do this. So the first thing we have to do is we have to understand this. We want to understand the good complex, right? So let's just recap what's going on here. So we want to understand TMF smash TMF. Say if we're going to understand the E1 term, we're going to begin with TMF smash Z, but that's the same thing as TMF smash yeah, that's what I want. TMF smash Z is K2, little k2. And so that's otherwise known as the connective Morava-K homology of little TMF. Okay? So the way we're going to think about it is the way I described. We're going to take little k2 star TMF, and we're going to map it to this big k2 star of TMF. Now this guy, it's the same thing as K2 star of capital TMF, if you like. I'll just write that. Same difference. And this thing is, as I mentioned already in response to Andy's question, it turns out to be a subalgebra of the Morava stabilizer algebra, which is K2 star E2. So this is the Morava stabilizer algebra. I'm sorry, can people see this down here? Sigma parentheses 2. I'm sorry for that. Let's see. And so this guy, so I'm going to think about the image of this in here. And so the image of this in here is something I'm going to call little sigma 2 twiddle, because it's a connective version of this capital sigma 2 twiddle. So that's the image of this in here. And then there's a kernel. And the kernel is this evil business. And then it turns out something really nice happens in this case.
Mark, is that sigma tilde, is there some description of it as an extended thing over a quotient quadrivoid or something?
We'll get there.
Oh, okay.
We'll study this thing until we're sick of it. So the thing that we find is that, in fact, if you take so you know, as I said before, you can take the whole E1 term of the TMF resolution for Z, and it will similarly surject onto something that is. So let's remember, we think of this sigma 2 twiddle, even though it has a lousy name, we think of it as being good. Okay, and this guy we think of as being bad. Okay, it's evil. Okay, and so similarly we have this thing surjects onto this good complex, and then the kernel is this evil complex. Okay, and it turns out that this good complex is actually nothing more. So this guy is itself a Hopf algebra. And this thing is nothing but the Kobar complex for little sigma 2 twiddle. And the co-module, which is its ground ring, K2 star. Okay? So the cohomology of the good complex is the cohomology of this Hopf algebra. So we really need to understand little sigma 2 twiddle. And we're going to have two ways of doing that. Two perspectives understanding little sigma 2 twiddle. So the first is the atom spectral sequence, the classical atom spectral sequence. That is, we're going to consider the so the classical atom spectral sequence, in the case doing a little change of rings theorem, looks like X'd over an exterior algebra on Q2 of the homology of TMF. And it converges to the little k2 homology of TMF. So now we have to compute this. Okay, so what is that? Well, it turns out this is like what Margolis homology is good for. So this is the Margolis homology, or otherwise known as the cohomology of the homology of TMF, where you endow it with the differential given by Q2, because Q2 squared equals 0. And then you take whatever you get and you tensor it with F2 adjoin V2. And so then this doesn't tell you all of X. There's also a contribution of X coming from the free summands in the homology of TMF as a module over this. And those free summands give a bunch of junk in X0. And that's that evil stuff I speak of. So plus this evil stuff. Okay. The second perspective, before I forget that I have two perspectives, the second perspective we'll take is that we'll explicitly understand this sigma 2 twiddle. And then we'll try and think about what little sigma 2 twiddle looks like inside of it. So let's continue with technique number 1.
Mark, in particular, there's no like B1 periodicity or something like that.
No V1 anything, no. It's just F2s. Just F2s. Okay. So now, though keep in mind that sort of V1's already kind of modded out because we're working with Z, where V1's been modded out. So we don't really have, but I mean, you know, the real player is V2, but V2 also is just V2 times anything, and capital V is 0. Right. So let's do this. So the Margolis homology. So the cohomology. So let's see here. The homology of TMF is A mod A2 dual, which is F2 adjoin zeta 1 to the 8th, zeta 2 to the 4th, zeta 3 squared, zeta 4, etc., where the zeta i's are the conjugates of the xi i's. And the coproduct for zeta I is zeta I, zeta 3, tensor zeta I minus 3 to the 8th, plus other terms that I don't care about. And zeta 3 is dual to Q2. And so what that tells me is that Q2 of zeta I is zeta I minus 3 to the 8th. The other thing to know about Q2 is it acts as a derivation. So this tells me everything. So then what happens? Well, zeta 4 kills zeta 1 to the 8th. Zeta 5 kills zeta 2 to the 8th, zeta 6 kills zeta 3 to the 8th, etc. And then their squares all survive. And so what I deduce from that is that the Margolis homology of TMF is F2 adjoin zeta 2 to the 4th, zeta 3 squared, zeta 4 squared, etc., modulo zeta I to the 8th equals 0. it turns out that this spectral sequence, then once you know this, there's no room for differentials. This thing collapses. So what you deduce from that is that the K2 star, well, it tells you sigma 2 twiddle. Remember, sigma 2 twiddle is just the V2 periodic stuff, right? So it's going to be, this is the stuff that's going to contribute the sigma 2 twiddle, and this is the evil stuff, right? So it tells us that sigma 2 twiddle is, it's F2 adjoin V2, adjoin some generators T1, so I'm going to give these kind of funny names. T2 twiddle squared, T3 twiddle, T4 twiddle, etc. Modulo relations Ti twiddle to the fourth equals 0. Where here the Ti twiddles are detected by the zeta I squareds. This isn't exactly true. I don't know this. The atom spectral sequence is only computing an associated gradient of sigma 2 twiddle with respect to atoms filtration. So Ti twiddle to the fourth is actually equal to something. I don't know what it is, but it has atoms filtration greater than 0. Because these Ti's are in atoms filtration 0. Okay, so that's actually all I know.
Probably some V2 multiple of Ti twiddle itself. Probably a V2 multiple of Ti twiddle.
Probably. Let's see about that. So let's investigate sigma 2 twiddle. So let's go to technique number 2. And technique number 2 would have me look at the sigma 2 twiddle, which we'll remember is K2 star TMF. And we're thinking about that as sitting inside of sigma 2, which is E2 star, K2 star E2. And so this is the guy that we know and love, the Morava stabilizer algebra, studied much by Doug and others. And this thing takes the form K2 star, the way I've set it up, K2 star join T1, T2, T3, etc. Modulo relations that look like Ti to the fourth equals V2 to some power Ti. Okay, so that's the source of Doug's comment, because he knows this. However, there's another perspective you can take on K2 star E2. What you can do is you can, let me just say it over here. If you want to take a more E-any approach, Morava stabilizer group approach, what you can do is you can let K2 star be this 2 periodic version of K2 that I think Agnes talked about. And then similarly we've got the Morava E theory. And what we know is that if we take K2 star E2, it looks like maps on the extended Morava stabilizer group valued in K2 star. And we also know that if I take K2 and take homotopy fixed points with respect to some group, C3 semi-direct Gal, this gives me K parentheses 2, and E2 HC3 semi-direct Gal equals E parentheses 2, K2 localized, and the HHHW03, some group of 48, is the K2 localization of TMF. So then I can apply descent to this statement over here, and I get some alternative formulas for these co-operations. I can also think about this as being the C3 semi-direct Gal equivariant maps from G2 mod C3 semi-direct Gal into K2 star. And I can think about these guys as being the C3 semi-direct Gal equivariant maps from G2 mod G48 into K2 star. Okay. Now, how are these TIs functions on this? So let me tell you, or remind you if you already know this. These are the same TIs that are in BP star BP. So what you do is you use the presentation. So remember this presentation that Vesna had in her talk. The Morava stabilizer group is the units of this algebra. And here O was like this Witt ring on F4, adjoin some S mod S squared equals 2, and this kind of thing for A and W. So then elements in here get written as A0 plus A1S plus A2S squared plus ... And what you do is you want to think about what does a TI do to one of these cosets. So say you have a G in one of these cosets. Then, well, the Gal cancels the Gal, and the C3, to get rid of the C3 action, just choose a unique representative such that A0 equals 1. So you make A0 equal 1. And when you choose a representative such that A0 equals 1, then TI on this coset is just the ith coefficient of this thing times u to the 1 minus p to the I. Okay, now I should mention this Witt ring looks scary, but it's not. It's just what you get when you adjoin a third root of unity to the two adducts. And these AIs, these are not just any AIs, they're Teichmüller lifts. These AIs have the property that they're either 0, omega 1, omega, or omega squared. Okay? So that's how I think of them as elements of F4. Okay? Okay, running out of time. Let me just say that so what you do is you're trying to understand G2 mod G48, right? Because we're looking at functions on this coset space. And you're like, well, gosh, I need to write down canonical representatives of these cosets, just like I was doing over here, okay? And so to do that, what you observe is you take the subgroup K, which is much studied by Doug Ravenel, Hans Werner Henn, many other people. This subgroup K of the Morava stabilizer group. This consists of all the G with the property that A0 equals 1, A1 equals 0, and you make A2 be either 0 or omega, but it's not allowed to be 1 or omega squared. And that turns out to be a subgroup. And And then when you take this K and map it to G2, and then compose it out to the quotient, it turns out this thing is a homeomorphism of profinite sets. Okay? I mean, this is not normal. This isn't a group, but this is a homeomorphism of profinite sets. So functions on them are the same. So we're going to understand functions on this thing by just thinking of them as functions on this K. Now, let me just say that what the real problem turns out to be that the C3 acts naturally on K because K is closed under conjugation by elements of C3. But a problem with K is it's not closed under conjugation by elements of the Galois group. So there's no real natural action of the Galois group on K. However, I've got a bijection, and I've got an action of the Galois group on this via left multiplication. So by merit of this homeomorphism, I have an unnatural action of the Galois group on K. And that's what I mean by the equivariant maps with respect to this acting on K. All right? So this turns out to be a major technical problem that we have to overcome. But I'm running out of time, thankfully, so I won't be able to belabor you with it anymore. Suffice it to say that if you look at this condition over here, then it seems like the functions of interest are, so I'll just assert that sigma 2 twiddle ends up being F2 adjoin V1, or V2, adjoin some, I already said it was adjoin some TIs, and I'll be able to say more about them. So T3, T4. We already introduced these TI twiddles. We just didn't understand the relations, and now we understand them a little better. And then I'm going to choose a very special representative for T2 twiddle. Namely, I'm going to take so T2 twiddle I'm going to define to be the function that is omega times T2. Sorry, omega squared times T2. It turns out that this thing is Galois invariant with respect to this weird action. And so then T2 twiddle squared is, when I make this definition, okay, so first off I want to say something over here. A slick way of writing this condition, that A2 is either 0 or omega, is to write A2 squared equals omega A2. That's the same thing as that. And so then that tells me that on this group K, T2 squared equals omega T2. And so this shows up in the green book in the definition of some Hopf algebra. And if I choose this slightly different guy, then T2 twiddle squared is T2 twiddle. Okay? And then I'm just going to point out, then it follows, V2. So there's a relation like this. And so then there's a V2 in there. And so then T2, I can square this. And T2 twiddle squared is V2 squared T2 twiddle squared. Okay, so I'm just pointing out I have a very explicit relation for this T2 twiddle squared, and then these other guys also satisfy some relations. So the other thing to note is that these TI twiddles for I bigger than or equal to 3 turn out to be equal to the TIs that I described before modulo terms of higher Adams filtration. Gosh, okay. So the upshot here is that I understand these TIs very well. I understand them kind of well, okay? I understand them up to correction terms and higher Adams filtration, but then I can use formulas in the Morava stabilizer algebra to understand things like the coproduct in sigma 2 twiddle modulo correction terms and higher Adams filtration, okay? That's the upshot of this whole discussion. It allows me to understand formulas with correction terms and higher Adams filtration in sigma 2 twiddle. Okay, we're after the cohomology of the good complex. And we're almost out of time. All right, so let's do this. So to compute the cohomology of the good complex, what I'm going to do is I'm going to, remember the cohomology of the good complex is the cohomology of this sigma 2 twiddle. And so I'm interested in the cohomology of this sigma 2 twiddle, which is otherwise known as the cohomology of the good complex for Z. And what I'm going to do is I'm going to take the associated gradient of this thing with respect to Adams filtration. And that induces a filtration on cobar complexes and hence a spectral sequence that I'm going to call an Adams filtration spectral sequence. Okay? And the upshot of this work that I did over here is I'm able to deduce differentials in the Adams filtration spectral sequence. Based on formulas, on sigma 2 formulas in the Green Book. And then to get at this thing, there's a kind of May spectral sequence that whose E2 term will look like F2 adjoin H22, H31, H32, H41, H42, etc. And here this corresponds to T2 twiddle squared, T3 twiddle, T3 twiddle squared, T4 twiddle, T4 twiddle squared, etc. That's where these generators come from. It turns out that this spectral sequence collapses. Okay? And let me tell you some differentials in the Adams filtration spectral sequence coming from sigma 2 formulas. It turns out that you have D1 of HI1 equals V2 HI2 squared, and D2 to the I minus 1 of HI2 equals V2 to the 2 to the I minus 1 I minus 2 squared, HI minus 2 1 squared. And I'm really running out of time in an extreme way, so let me tell you roughly what you get out of here. This tells you that the cohomology of the good complex is very roughly something like F2 adjoin V2, tensor and exterior algebra on H22, H31, H32, H42, plus F2 adjoin V2, adjoin, so here these xi's are HI1 squareds, x3, x4, etc., modulo some relations that say that v2 to the 2 to the I minus 1, xi equals I plus 1, xi equals 0, coming from that second differential. And then there's, let me kind of put this in quotes, tensor some kind of exterior algebra on some generators that I'm going to be kind of non-explicit about, if you don't mind. I mean, the HI2s supported differentials, but them times some things turn out to not support differentials, and this kind of describes the size of this term, plus some V2 to the 1 torsion. So although the good complex is V2 periodic, its cohomology, this is the only part that's V2 periodic. And this term here is V2 torsion, but the V2 torsion is kind of long, and then you have this short V2 torsion, is roughly the gist of it, okay? All right, now I want to point out something. I want to point out that you can then localize this you can invert V2. And that will be the E2 term for the capital TMF guy. So that is F2 adjoin V2 plus or minus 1 tends to an exterior algebra on these four generators, H22, H31, H32, H42. Now you might say, whoa, yeah, well, didn't Bhattacharya-Egger do that? Yeah, they did. So this is another way of doing this computation. And we get the same answer, which is good. But more importantly, we can now compare the TMF atom spectral sequence with the capital TMF atom spectral sequence. So I'm essentially out of time, but let me at least show you what happens when you do that comparison. So could I have the projector, please? Okay. I assume there's some light switch I should turn off. Oh, wow. Okay, never mind. It's done for me. Magical. Okay, great. Wonderful. Thank you. So I'm not really expecting that this is a picture that can be parsed too much. This is a picture of this Agatha-cockological spectral sequence business. It's a picture of Ext. The only takeaway here is that it gives us this bunch of red dots. And those red dots is the cohomology of the evil complex. So ignore this slide. Okay, this is the slide I really care about. This is the E2 term of the TMF-based atom spectral sequence. Actually, it's not technically the E2 term because it also involves some D1 differentials, but those are the connecting homomorphism between the cohomology of the good complex and the cohomology of the evil complex. So those red dots are the things pulled from the last slide I told you to ignore. And the rest of the dots is the cohomology of the good complex. And what I've done is I've drawn in some differentials, okay? And these differentials, well, let's not even talk about where they come from. But I just want to point out one thing. So we did this computation through the 45 step. And here's the Bhattacharya-Egger computation. This is taken from Phil Egger's thesis. So these are the possible differentials. You don't need to worry about the one supported from the zero line because you know by the existence of the unit that has to be a permanent cycle. So that one's not there. You're worried about that other one. That generator's name is H32. And so then you see that in fact, even in this small range, although H32 supports a differential, V2 to the third H32 does not. And well, V2 squared H32 supports a D3 differential. So and so then you could multiply that by V2 because V2 is a self map. And so that would say then D3 on this would be V2 times that dot. Oh, but it's evil, so V2 times it is 0. So therefore it can't. D3 is 0 over here, and there's nothing above there. So therefore this guy's a permanent cycle. So then that shows that there is no differential. And this spectral sequence that I showed you collapses. I promised you something about the telescope conjecture, but I totally ran out of time. So I'll just say this. This particular element over here, if V2 to the I on this element is non-trivial for infinitely many I, it's only in pi 32. Look at that. If V2 to the I on this element is non-trivial for arbitrarily many I, the telescope conjecture is false. But of course, we don't know that. All right, I'll end there.
Any questions left open?
What do those slides look like? It was green to play and mate in 7 moves or something like that.
That was Phil's slide. It looks like a chess problem, doesn't it? Well, I'd like to thank all you guys for an amazing week. This has been like every day, the talks have been mind-blowing, and I've learned so much. So thank you guys.